Hi, everybody. This is the video that is accompanying your energy notes. Now, these notes are coming kind of secondary. The week before, you guys did have some links to go through, video links and reading links to kind of get you started with this energy concept. So much of what is starting the notes, I'm just going to have you read through because a lot of the information you actually kind of alluded to when you did your different discovery pre-assessment labs. So many of you talked kind of about this very first slide, where if we're talking about energy, we're associating it with forces. And if we have forces, we have kinematics. So everything that we've talked about is kind of culminating together into this topic of energy. Now, one of the things I do want to note in this first slide is that energy is a scalar function. So energy in itself doesn't care about direction, it just has magnitude. So it is only how much do I have? You don't have negative energy because energy is something that is just contained within a system via one form or another. One of those being potential energy. Our focus is potential energy based on height and based off of the gravitational pull. So we have the equation U is equal to mgh. Do note that the units for energy are a joule, and it is kind of the short version of writing kilogram meter squared over second squared. Along with the fact that energy is a scalar function, it also does not care about path. So we've had the discussion of path before. In Unit 2, we looked at Dorothy versus Toto. And that discussion really sparked, hey, what is the difference between distance and displacement? Where distance cared about path, displacement only cared about your initial point and your final point. That's the same thing with energy. Energy doesn't care about what you do in between. It just wants to know, where did you start versus where did you finish? And with that comes the conversation of forces. So there are some forces that care about the path and some forces that don't. Forces that don't care about the path or path independent are conservative forces. Forces that do depend on the path are non-conservative forces. Now, I would like to use this time to go over the examples. So you can go ahead and read example 1. And what we're going to notice here is that if we're looking at how long something is going to take, well, then we're looking at time. So we obviously know that kinematics are going to come into play, but energy is also going to come into play. So that's how we're going to start this problem. We know that U is equal to mgh. Well, we know U, we know M, we know G. We can solve for H. But what is H going to give us? Well, the height that the cat is going to start at is also the cat's initial position. So that height that we solve for becomes xi, and using kinematics will allow us to solve for time. I do apologize that I am kind of going quickly through these. I only have 15 minutes allotted or allowed in the video. So if you have any questions on any of this, one, pause the video and actually look through the work, and two, send me an email and we can talk about any questions that you may have. So this is your example just using potential energy. So really, something that's path independent because it was a gravitational force, and using that information with kinematics, we can solve for time. Now, the next thing that we could talk about is kinetic energy. So the energy that you have that is associated with motion. So K is equal to 1/2 mv squared. We can use this in example 2 where we're looking at the train. Now, the train has kind of 3 parts to it. The first part, we always start with energy. We always say, okay, well, we know that this is the energy unit. Typically, energy is the line 1 of our problems, but we do line 1. We say, all right, K is equal to 1/2 mv squared, and then we go, I have 3 unknown variables. So 3 question marks, 3-step problem. So we're looking for K, but the other thing is we don't have mass. Well, we may not have mass, but we have weight. And we know that Fg is equal to m times g, so we can solve for mass using line 2. So we did that, we used forces, but we also don't know the final velocity that the train gets to. Well, kinematics come into play. We know that the initial velocity was 0. We know acceleration. We know time. We can solve for the final velocity. So using forces and kinematics, we put those two numbers into our energy equation and we can solve for K. Which brings us to mechanical energy. So if we wanted to know the sum of all of the energy that an object contains, we would want to add the kinetic plus the potential energy it has. It's very rare that you're going to just have one or the other, especially in our topics. We're looking at things constantly moving. Well, when it's moving and it's going up and down a ramp, or it's going in circular motion, you have different heights, you have different velocities, so therefore you're going to have mechanical energy. Now, the one thing to note is that energy cannot be created nor destroyed. As many of you said, it can only be transferred throughout the system. So this principle, much like matter, where matter cannot be created or destroyed, it's just converted into different forms. This is something that you are familiar with, but now I'm going to give you an equation. So this truly becomes your line 1, because we're going to be looking at an object moving from that initial position to that final position. And how is that energy transforming between initial to final? So this is what I should see you writing down. Every single time you approach an energy problem, you start with initial kinetic plus initial potential is equal to final kinetic plus final potential. Because if it's only transferred, then you have to see that transfer from the initial to final. Using that, you can go ahead and take a look at example 3. You're probably going to want to pause this video and then take a look at my work. So we start with our line 1, and you'll notice that I cancel out anything that's equal to 0. So in this problem, the coaster starts at the top of the highest hill and pauses. So if you pause, your velocity is 0. You're initially starting with 0. So 1/2 mv squared, if v is 0, then your whole kinetic energy is 0. So I'm just going to cancel that out. And we do have an initial height. We will be moving when we approach that hill too. And then we will have a final height. So those are kind of the two questions that you want to ask when you do this line 1. Do I have a velocity? Do I have a height? Because if either one of those is no, I don't have a height, well then I don't have potential energy. I don't have a velocity, I don't have kinetic energy. So cancel things from the start to make your life easier. So we do that, we say, okay, we have these 3 things. Then what I want to see in your line 2 is you breaking down the equations for kinetic and potential energy. So we have mgh is equal to 1/2 m multiplied by your final velocity squared plus mghf. Notice that I canceled all of the m's because if something appears in every single part of your equation, then it doesn't actually do anything, and you are allowed to cancel them. Now, for this problem, you did have m, but sometimes you don't. A lot of problems don't give you m because you're able to cancel. So just remember that if you kind of get stuck on any of those practice problems, you most likely can cancel out your m. So once I do that, I look and say, okay, well, what variables do I know? What don't I? And I'm left with 2 question marks. 2 question marks means a 2-step problem. So the overall goal of this problem is to solve for h, and we don't know VF. Well, as soon as I see V, I'm thinking, hey, I need to do kinematics. So I go down here and I say, all right, well, I need acceleration and I need time. Well, I know delta x, so I can use this equation first, solve for A, and then solve for VF. At this point, I have everything I need to plug back into that equation, and I'm able to solve for the initial height. So notice that I always start energy first, and then see, okay, do I have to do another step? Yes. Here I'm going to either use forces or kinematics, and then I'm going to finish with energy. Now, the very last thing is the concept of work. So what is actually transferring, or how are you getting from that initial stage to the final stage? Something is getting you to that point, and it's the concept of work, and it is the process of transferring you from that initial to the final stage. Work has the equation of force multiplied by delta x. So how much force do you need to apply over how much of a distance in order to get you from the initial to the final stage? Now, work and those forces are only for conservative forces. Conservative forces are the only forces that do work. Or I'm sorry, non-conservative. I hope I said that. Non-conservative forces are the only forces that do work. I apologize if I mistakenly said conservative. It is non-conservative forces do work. Conservative forces do not. Gravity does pull you down, but it's not exerting anything to get you from that initial to the final stage. Whereas non-conservative forces exert energy in order to get you from that initial to the final stage. Now, here you can go through a couple kind of discussion and example points, but really what our focus is on the final form of the conservation of energy equation. So we have Ki plus Ui plus that work, what is getting you from the initial stage to the final stage, is equal to Kf plus Uf. Now, why did this change from a couple minutes ago? A couple minutes ago, the work that was done in all of those problems was by conservative forces. And conservative forces don't do work, so that pretty much just went to zero. Now, let's look at this example. An arrow is fired from a bow whose string exerts an average force of 95 newtons. As soon as you see that it's actually talking about a force, you know that work is not equal to zero and it's going to be in the equation. So we start with Ki plus Ui plus work is equal to Kf plus Uf. We say, all right, well, I pull it back and I'm holding it. So if I'm holding it, initial velocity is zero, Ki goes away. Your potential energy from the initial to the final stage is going to be zero because you're only looking at that release. So from here to here, you don't have a height change. So if you don't have a height change, then you don't have any potential energy, which means you're just left with work is equal to Kf, because it is going to leave at some final velocity, but some force pushed it to that final velocity. So we are left with F delta X is equal to 1/2 VF squared. And for this problem, we can just plug right in and we're able to solve for velocity. Now, the next problem is a little bit more challenging because it involves multiple steps, but notice still that my step one is the same. So I start with my line one, Ki plus Ui plus work is equal to Kf plus Uf. I say, all right, what do I know? What do I need to find? Well, I know that I'm trying to solve for work. Notice that it is negative because the work is being done by the brakes. So work is the one type of energy that does care about positive or negative. It's positive if it's taking the energy in, but it's negative if it's doing the work. So just think about your free body diagram. If it would be negative on a free body diagram, like the brakes would be because it's going against your motion, then that force is going to be negative, that work is going to be negative. Now, I also don't know the initial height, but my handy dandy triangle is able to allow me to solve for that. So delta X is going to be your hypotenuse. The height is what you want to solve for. You can use your trig function and then use that value, plug it into your equation. You're good to go for work. And the last problem is on your own. Notice that this problem is going to involve your trig function, kinematics, and energy. So you can try this problem on your own, check your answer, email me if you have any questions. Thank you for the quick set of notes that we just went through. Please let me know if you have any questions, and you also have those other resources that will kind